Hello everyone. Here is another problem on mesh analysis with dependent sources. Having done two examples, I thought I would take up one more so that the understanding becomes good. See, here is another problem wherein we have one independent source and one dependent source. If we look at the network, it is very clear that 0.5 V1 is a dependent source. This is a current source. As we can see the arrow within it, it's a current source having a magnitude of 0.5 V1. So what is V1? V1 is the potential difference across this 2 ohm resistor. So whenever current flows through this 2 ohm resistor, there exists a potential difference across 2 ohm resistance, and that voltage is designated as V1, and the 0.5 V1 or V1 by 2 would be the magnitude of this dependent current source. Now what is the thing that we are supposed to find? We are supposed to find V1. So in this problem, V1 is supposed to be determined. So the problem says determine V1. So how do we do this problem? Okay, as I've told already, one can approach the problem by different ways, loop current method or mesh current method. Node voltage technique are the popular ones. One can adopt any method and then do the problem. All right. So if I can take up this problem on, let us say, node voltage method, I would make this a datum node. All right. So with respect to the datum node, the potential of this node obviously is plus 100 volt, because the potential difference between this node and the datum node is 100 volt, and when the one end of the voltage source is taken as the datum or the reference, which is supposed to be at zero potential, the other one is at plus 100 volt. All right. So similarly, extending the same logic, the potential of this node is V1. Okay. So the potential of this node is not known. I will name it as V2. Okay. So I will formulate equations and then try to solve the problem. Okay. So if we can write the equations, we can write it by inspection. You can write the nodal equations by inspection. For a change, we will try by inspection. All right. So it is the node V1 into the sum of the admittances at that node, that is V1 multiplied by, what are the sum of the admittances? It is 1 by 12 conductances in this case. Admittances is a generalized word, but then which is reciprocal of impedance, but then when we are seeing resistances in this network, we can even call it conductance, as a specific case. This is 1 by 12, sum of the resistances, or rather sum of the admittances, conductances. All right. 1 by 10 plus 1 by 2. It's the sum of the conductances meeting at node V1, node 1. Okay. So V1 into that. Okay. Minus the conductances common between, sum of the conductances common between node and node 2. That is our 10 ohm. With a negative sign, if we have to take it up, it's 1 by 10 into V2 equal to the current entering the node V1, node 1. What is the current entering? Current entering would be 100 divided by 12. 100 divided by 12. This is the equation we get. All right. So this we have written it by inspection. One can even write from first principle also. That is also acceptable. You will get the same thing. Okay. From the first principle, if we have to write, it is the various currents meeting at the node 1 is made 0. All right. That way also one can do. So if you can simplify this equation, you will get this equation to be equal to, with the help of a calculator, if I do it, I get this as 0.68 V1 minus 0.1 V2. I'll get it as 8.33. This is my equation 1. So I've got an equation in V1 and V2. So I need to get one more equation because you have two unknowns. We will have to get One more equation. So what is the other equation? We will write the nodal equation at node 2. This is your nodal equation. This is node voltage equation or nodal equation at node 1. Okay, whose voltage is V1. Now we will write nodal equation at the other node. Nodal equation at node 2. How do we write it? At node 2, I will write sum of all the conductances common between node 2 and node 1 with a negative sign, that is minus V1 divided by 10. Rather, 1 by 10 into V1 plus sum of all the conductances meeting at node 2. What are the conductances meeting at node 2? One is 1 by 10, another is 1 by 6. This multiplied by V2 equal to the current that is pumping into the node or entering the node, that is 0.5 V1. Alright, so let's try to simplify this equation. If I simplify this equation, what is it I get? I will shift this 0.5 V1 onto the left hand side. I already have minus 0.1 V1, 1 by 10 is 0.1, and 0.5, I suppose that would reduce it to 0.6 V1. This is a simple simplification technique. There is nothing complex about it. One can easily comprehend. Equal to 0. This is my equation 2. Now we will solve equation 1 and 2. We have calculators to do it. We need not bother much. Okay, we will solving, what is it we get? If we can solving equations 1 and 2, we will have to do by Cramer's rule. So solving equations 1 and 2, you will get V1 to be equal to 18.33 volts and V2 equal to 41.35 volt. So these are the results that we are able to get. Two equations and two unknowns. We should be able to get it. It's not a problem. For those of you who do not know as to how to apply Cramer's rule, maybe a trivia will help. Perhaps maybe I'll do that also. So that for people who don't remember, for their benefit, let me do. I have pasted equation 1. I'll take equation 2. I pasted this underneath. Okay, how do I apply Cramer's rule? It is simple. I will have to find out V1 to be equal to, if I apply Cramer's rule, so V1 equal to, we need to write the ratio of the determinants. What determinants? So you have one numerator determinant and another denominator determinant. Okay, so what is denominator determinant? It is 0.68, which is what we call as discriminant, minus 0.1. This determinant is obtained by taking the coefficients of V1 and V2 from both the equations and arranging them in row wise. Okay, so I've taken the coefficient of 0.68, minus 0.1, minus 0.6 and 266. I have arranged it this way, this determinant. So the numerator determinant is delta. In the delta determinant, the first column is replaced. That is, first column is, it's replaced with the right hand side coefficients. 8.33 and 0, this is 1. And the other coefficients are retained, 0.1 and 0.266. How do we expand this? We know how to do this into this minus this into this. That's how we do the Simplification, one must be knowing this. These are all elementary things which we perhaps study in high school. Still, 8.33 into 0.266, and 0 into something is 0. In the denominator, we have 0.68 multiplied with 0.266, minus of minus, that is plus, and again that will be minus 0.1, 0.6. So this is how you calculate. So that's how we get V1. Okay. Similarly, how do we get V2? V2 is, it's done similar to V1. Only thing is that the numerator determinant gets replaced. V2 is, what I'll do now is, the delta determinant, I'll replace the second column. Delta is maintained as it is. This is your delta determinant. Delta determinant is maintained as it is, but in the delta determinant now, the first column is maintained, second column is replaced with 8 right hand side terms of equations 1 and 2. You do like this. Okay, the delta is same. So this you will get it to be equal to, this also you know how to do. You will get the value to be equal to 41.35. So this is how you do. And this you will get it to be equal to this. I'll have to get it as 18.33. Okay, so one can do problems of this nature. It is very simple. Okay, so here we are given a network like this, a key recap. Okay, a network like this, so wherein we are supposed to determine V1. Okay, so how to determine V1? So I resorted to nodal technique. I've taken one of the nodes as the datum node and then formulated the equation. All right. By inspection for a change, if you're not able to write the equations by inspection, please see similar problems. I have done similar problems and uploaded. You can see them. Okay, so that I have done by first principle. Here I have done it by inspection. Whichever method you do, however you do, you arrive with the same equations. Okay, if you can write by inspection, that is also fine. You'll get the same equation. Okay, so you are able to write two equations at two nodes based on fundamentals, then you solve and you get the values. So our unknown is V1, that is 18.33 volts. So the answer is 18.33 volts. V1 equal to 18.33 volts. So problems of this nature, it is similar to how we do with independent sources. You can conveniently do it. Okay, I'll take up more problems on dependent sources. Maybe some problems on theorems would help us understand these dependent sources better. In competitive exams, problems on dependent sources are invariably asked. So one has to be quite comfortable and one has to get used to solving problems on dependent sources. Thank you for watching. See you on the next video. Bye-bye.